This presentation is delivered by the Stanford Center for Professional Development.
Okay, so I think that's all I have for administrative stuff, and I guess we'll finish up this this topic of truncated Newton methods, and then we'll go on to truncated Newton interior point methods. So we'll finish up another chunk of the class today, which is, and then we'll move on to yet another chunk. But the chunk we're going to finish up today is basically how to solve extremely large problems. So, okay, so let's look at let's go back to truncated Newton method. So remember what truncated Newton method is. It's you form you're minimizing a smooth nonlinear convex function, and you form the Newton system, but instead of solving for the search direction exactly by, for example, a direct method that would do some kind of direct factorization or something like that. Instead of doing that, what you'll do is use CG or PCG, preconditioned CG, to approximately solve the Newton system. Now, the way this is done is a bit surprising. What you don't do is actually spend all this, you don't do enough CG iterations to actually get a good approximate direct solution of the Newton system, because there's no point. Because in fact your goal is not to solve the Newton system, your goal is to minimize this function. So in fact these things work really well, and in fact they work well precisely when a reasonably good search direction emerges after a shockingly few number of CG steps. So that's generally how these things work well. Okay, so this is an example. I think it's a logistic regression example with L2 regularization. It really doesn't matter because it's kind of similar no matter what problem it is. So here's what we'll do. The problem was scaled in such a way that we could pull off Cholesky factorization. I think the Cholesky factor had something like 30 million non-zeros. So it'll take some time to do both the Cholesky factorization and also to do the backward and forward substitution. So, but direct is possible. All we have to do with this problem is scale it by a factor of 10, and direct becomes kind of out of the question. So then at least on a little standard machine. But we'll compare that with a truncated Newton method, where we do several things here. What we're going to do is we're going to simply do 10 steps. This says we'll exit if we actually do solve the Newton system within 0.01%. Is that right? Yeah, 0.01%. Or if we hit 10 iterations. So almost always this is going to be 10 iterations. The second one essentially does 50 iterations, although we will terminate early if we solve the Newton system. And the third one will do 250 steps. Now, I guess in this problem I forget how many variables there are, but it's on the order. I think it's tens of thousands or something like that. I actually don't remember. Well, here we go. Yeah, it's on the order of tens of thousands. Okay, so maybe it is 10,000. So it's 10,000 is the size of n. So let's bear in mind that the theory says that if you do 10,000 CG steps, you will get the Newton direction. So by the way, the practice does not conform to the theory. The theory tells you get the exact Newton step. If you did 10,000 steps in perfect arithmetic, in exact arithmetic, which of course we don't. All these are done in doubles, obviously. So, but the point is, this number is shockingly shy of the number that theory tells you will do the trick. And these are like a big joke, right? That's 1,000th of the number of steps required. Now, on the other hand, if you remember all this business about the spectrum, that's going to be important. So the question is really, the 10,000 says that no matter what the right-hand side is, and for any a, you're going to get the exact solution. But the point is, in 10 steps, you'll get a reasonable solution provided certain things happen. And if the spectrum is clustered, if the right-hand side, which is the gradient, lies in the, a lot of it lies in the 10th Krylov subspace, that'll do the trick. Several things will work. Okay. So here's how it works. Here are the iterations. And let's see, here's the Newton method, which does what we all would expect it to do, which is basically nail this thing in 16 steps to some accuracy way beyond anything you need. So that's our friend Newton here. By the way, that's Newton applied to a smooth convex function. So Newton doesn't work this way in general. But okay. If you do 50 steps, let's see. The CG 250 is right on top of it. here. So if each of the, what that says is that the quality of the search direction you get in 250 CG steps is whatever that search direction is, although no one would claim it is the Newton direction, whatever it is obviously good enough to provide exactly match the performance of the Newton method, right? So this alone is just gonna beat Newton's method insanely, both in memory and in time. But the really interesting part is if you do 50 CG steps, you can see you're not doing, you're down here, it's charging you one more. So that's even more shocking because that is now 1/5 the effort of this one. And the real shocker is this one where you do just 10 steps. The 10-step one, actually, if you truncate around here, which is actually probably a perfectly good accuracy, is actually is amazingly good. I mean, this is actually sort of amazing up here. Okay, now the real measure in a method like this is absolutely not the number of iterations. That's totally irrelevant. What's irrelevant is the number of CG steps, because the CG step is what makes it makes a call to a Hessian multiply method, right? And I mean exactly what I said. You generally don't form the Hessian and then multiply it by a matrix. You're welcome to do that. There's cases where you would do that, but it's remember that the interface of a truncated Newton method to the problem is simply you need something that will multiply the Hessian by a vector. Period. That's all you need. You don't need anything else. So in this case, and this, by the way, would correspond extremely well with just time. So this tells you how fast it is. And you can see something shocking, that the 10 steps of CG here gives you, if that's a good enough accuracy for you, it does this in just a shockingly small number of steps. So that's CG. This is very common. I guess it's called, sort of on the streets, it's called jamming. The theory would tell you that if you did things in infinite precision, which you don't, that this would eventually converge. Of course, it might take a long time or something like that. We don't do things in infinite precision, we do things in doubles. And so, in fact, it might just stay here. In any case, for all practical matters, you're just wasting your time out here. Yeah, by the way, this is going to be a number so small that we're talking, well, we'll see in a minute what the ratio, how much faster this is than a direct method. So you see actually everything you see that is typical. This is quite typical. You get extremely good convergence. The width of each of these guys is 10 steps. The width of these is 50. They could be a little shorter than 50. They would be a little shorter than 50 if basically you solve the Newton direction. Now what I should have done is I should have shown what happens if you do CG1. I don't know why I didn't put it on this plot, but CG1 is basically a scaled, no, it's not even a scaled gradient method, it's a gradient method. And CG1 actually goes like this. Maybe it goes like that and then stops, like that. Okay? So, which is to say it's quite useless. Okay. So, here, I won't go, we looked at this last time, but these will just give you some numbers here. But the ratios are pretty good. There are things like speed-ups of 400 to 1 here. And let's actually see what happens if you put PCG in. PCG is what you need, a preconditioner is what you need to sort of eliminate that jamming type thing. And so if you put in a preconditioner, what happens, it's not too surprising, is now your CG thing, despite the fact that you're doing 10 CG steps, only 10 CG steps, you're actually getting a more than good enough search direction here to get extremely good performance in some just shocking number of steps. By the way, that's whatever that is. That's something like 100 and something steps. Each step is basically a matrix vector multiply, which you don't even implement as a matrix vector multiply in most cases. In fact, that's the whole point. So this is just a shocking number of a shockingly small number of steps to do this. Okay, so and if you want to see sort of what the numbers are there, they're not bad. They're things like 400 to 1 or something like that. These are good speedups. By the way, here the only thing we did was we didn't really want to wait more than an hour or something here. So that's the only, we set the problem size so that this would be like an hour. The same problem, which I guess you have all the source code for because it's on the website, I promise you, you could go in, make it 10 times bigger, and the CG stuff will run just fine. So, and then you'll be solving problems with, you know, a couple 100,000 variables. You can almost certainly take it to 1,000,000, and it'll just run. And it'll probably take, maybe it won't take 200 PCG passes, but it'll take something like 300 or something like that. Something just amazingly modest, and it will work. So, okay. So there's a lot of extensions here. You can do the things with equality constraints. If you use an infeasible start Newton method with equality constraints, you have to your equality constraints are actually not going to be guaranteed to hold, right? Because that's a property of if you take a step of 1 in a Newton method, your equality constraints hold. In general, if you do a truncated Newton, it's going to just simply converge to 0. And of course, you can take this idea and put it into a barrier method or your favorite or more sophisticated primal dual methods and so on. And I should also say that the distinction between direct and indirect methods is a nice gray boundary because in fact, the ones you've been using, SDPT3 and Sedumi, when they use nominally direct methods. And in fact, you can even see if you look at the right-hand column when you run CVX, you'll see. We didn't write. I mean, this is someone else's code, but in all of those things, they'll actually do several steps of iterative refinement. And what that means is they'll do a Cholesky factorization, but they will presume that there are numerical errors in it, and they'll simply use that as the preconditioner, and they'll do like 2 or 3 steps. So there's a sense in which you've actually already been using CG. But at the other extreme, this is where you calculate an extremely good approximation of the solution, and you have an amazingly good preconditioner. The things I've been showing you are at the other end, where you are computing, you're doing a really bad job of solving a gross approximation of the Newton direction, but it's good enough to make progress overall. Okay. So the last thing we're going to do is just apply these ideas to interior point methods. So what's going to happen? I mean, you're going to do. It's going to be tricky to do this, but it can work well, and that requires luck, tuning, and a good preconditioner. So those are actually generally bad qualities for an algorithm to have, right? Imagine if every time you called eig or a\b, there were 14 parameters you had to adjust, and you had to say, oh, a\b is not working, and someone says, no, I know how to do it. You have to go back and set eta a little bit higher for problems like this, and then watch it, and it runs for a while, and then jams, and then you have to come back and you go, no, restart it and set alpha to 0.01 and see what happens. I mean, so these are bad attributes. Actually, they're good attributes from an employment perspective, because it means whoever needs to run these things is going to need to pay someone to be there to babysit it. So these large-scale methods, they will need tuning at a minimum. Once they're tuned, they may not need babysitting and stuff like that, but they're so. Just to make it clear, these are not good attributes of methods. On the other hand, you shouldn't complain if you're solving a problem with 10 million variables or 100 million variables. So that was, you made the mistake by going into a field where such big problems had to be solved. So you can hardly complain then that you have to tune and baby, and that generic software off the web doesn't just work for you. So, okay. So we'll look at network rate control. This we've seen a whole bunch of times, and the problem is this. You want to maximize a logarithmic utility, so that's maximize the product of a bunch of flow rates. I have a matrix R, which has got 0, 1 entries, and it tells you, if you sum, RF calculates the sum on F. Each row of R actually gives you the links. It's got ones in the places where that flow goes over that link here. So, and then that's a capacity. So this thing is the total traffic. It's a vector of the traffic on each link, and that's the capacity on the link. And so the idea is a whole bunch of flows are sharing resources. They're sharing the links. The constraint is the capacity on the links, and we want to work out the sharing in such a way that this utility is maximized. This is the negative utility here. So that's the problem. It's sort of a classical. Actually, we've already seen this problem for distributed methods. We've seen that. The dual rate control problem looks like this. We've already seen this. You maximize n minus c transpose lambda plus, and then you get another log term here, and that's subject to lambda positive. Now remember the distributed method. So distributed rate control works like this. It solves this dual problem in a distributed way using a projected subgradient method, although of course the objective is differentiable, so it's really a projected gradient method, although that means something else, and it's not the algorithm we looked at before. And the duality gap is simply given by this. If you have if you have both a primal feasible flow, and if you have a dual feasible lambda, then this is the duality gap. So the primal dual search direction, if you just work out what it is, it doesn't matter because all of these search directions end up looking the same. So if you use a primal barrier, dual barrier, all of these things, if you apply a Newton method, they all look the same. They might be a little bit different and everything, but they all have the same components. Actually, they all look like this: a diagonal plus R transpose D2 R, just period. And that's for all methods. This is going to be for primal dual method. What will happen is the D's might change a little bit, the right-hand side might change a little bit, and so on, but otherwise they're going to be the same. All right, so once you solve this to get delta F, this is a block elimination method, and then you get delta lambda this way. And then these are just the details for this this dual primal dual search direction. You don't have to. You can just as well use you can just use a primal method. It makes no difference. The primal dual residual is this. You break it into two parts. That's the dual residual, and that's the centering residual. And then the algorithm just looks like this. This is the standard one. If you solve this exactly, it would be a primal dual method, and you'd expect it to converge in whatever 30, the usual 50 steps. But instead, we're going to solve this system here approximately using PCG. And then you do a line search on the norm of the residual, which is standard, and so on. Okay. So here's a problem instance with, let's see, 200,000 links and 100,000 flows. So that's it's a reasonable size problem. And there's about each flow has a length of about 12. So each flow goes over 12 hops, 12 links in the network. And each link has got about 6 flows on average going through it. We made the capacities random from over a range of 10 to 1, from 0.1 to 1. Here, the truncated Newton method is done with the following. You stop at either 10% accuracy, or that's the approximate duality gap divided by the dual function level, and you have an Nmax. This actually, in this case, Nmax was never reached. So, by the way, you might wonder where this is. This is kind of when you enter into how to make these things work. How to set these things. There's a lot of lore, so it's a lot of room for personal expression. So when you use these methods, all the art comes in figuring out a good stopping criterion for CG. And the idea is completely obvious. What you want to do is you want to do the smallest number of CG steps. You want to do the crappiest job of calculating a search direction that you can that will make the overall master algorithm work reasonably well. And you always start by looking at smaller problems and doing lots of CG steps, because if you can't make that work, then you're in trouble, big trouble. So once that's working, then you start backing off and start pushing things to the limit. And then only later, when you dare, do you get down to things like numbers of CG steps like 10, stuff like that. Okay. This uses a diagonal preconditioner. It uses a warm start, meaning that it starts it actually starts obviously from the last search direction, and then these are the parameters here. So here we're going to go to a 10 to the minus 4 suboptimality, which really isn't needed, but anyway. And here it is. So these are minus u of f. So these are the primal values and the dual values coming up like this. And what's really ridiculous about this is in 100 PCG steps, you basically have a very good you basically have optimized the flows. You've certainly optimized them within, in a couple hundred CG steps. Each CG step, by the way, is actually a forward. It's actually you multiply by R and R transpose. Those have physical meanings. R1 sums for each flow. It sums some numbers across the flow, and then R transpose simply calculates the traffic on an edge. So it's literally 200 passes, and it's all over, up and down. So you 200 passes up and down, and it's globally optimized. So, okay. This shows you the duality gap evolution here. And you can see actually that it's actually slowing down. Of course, if you do a primal dual method, you expect to see, with exact Newton, you expect to see something that looks like that. This is doing the opposite. It's slowing down. By the way, I think this duality gap is already pretty small. The reason is this is the total duality gap. What you should really report is the duality gap per flow. And there's 100,000 flows, roughly. So this is actually like 10 to the minus 8 here already, or something like that. That's the duality gap per flow. Meaning that I'm not even sure why we're showing this, but it was kind of all over about right here. So, okay. Here's the same problem with 1 million edges and 2 million flows. So these are getting, these are real problems. These are big problems now. These are not, you can't type this into CVX or something like that. And they're big. So, and that's the same thing. And it's just to show that it actually works and so on. And here's the duality gap. And again, it's, I guess it's slowing down or something like that, but it's good enough. This is completely ridiculous, right? The idea that maybe that you've got an extremely good solution, provably so, in 200 passes up and down across the network. I mean, that's really quite ridiculous. So, okay. So that finishes up this. I should say a little bit about this. I mean, there's a lot of art on this, and if you just go to Google and type in any of these types of strings, other names would be limited memory, BFGS, and it's got all sorts of names. Truncated Newton, iterative Newton. If you type in any of these things, you'll start looking at some of the lore, and sometimes they flatly contradict each other. There'll be one book will say you should make your stopping criterion for PCGs go this way, and another one says it should grow. I mean, so clearly no one has any idea, and you just deal with each problem on its own. So, okay. I should say one other thing is that I personally am no expert on large-scale optimization. But just for fun, a couple of years ago, we decided we would just do some just to see how it works. And I can say the following. I'm reasonably comfortable saying now, I don't know of a problem where we've never failed, ever. So we did a couple of machine learning problems, some finance problems, some control problems, did some, let's see, what else did we do? Circuit sizing and stuff like that. Yeah, the details differed every time. Took one grad student week. That's a unit of time. That's a unit of time to a unit of effort, I should say, to tune things. But no problem. I would just, come in one day, and some grad student, when I would come in the morning, they'd be leaving, and they'd say, "Good news, this PCG update rule nails it across a huge number of samples." And so anyway, so I think the bottom line on this is pretty simple to say. It's just this: if you have a problem that's in the million variable, 10 million. Now, of course, all of this, if you want to go much higher, no problem. But everything's going to come down to your ability to do this matrix to actually, to multiply by the Hessian. So you want to get a huge, super gigantic problem, and you want to take 1,000 of your closest friends' processors and make some giant MPI thing. I don't see any reason why it won't work. I just don't see why it won't go to 100 million variables or something like that. So then it's nice to know that if you have a problem and you solve small instances of it with CVX and you like what you see, and it looks good and promising, it's nice to know there's actually a path to full large-scale things. So, and I think that's really the takeaway message here. Okay. this finishes up one whole section of the course. It is on solving giant problems on a single machine, although it doesn't have to be a single machine, in a sort of centralized way. It is actually centralized because the CG algorithm is centralized. When you there's inner products are the parts that are centralized, but I don't think it's that big a deal. I don't know, if someone wanted to do this, it's not a big deal. They're scatter gather operations. If you're only doing a couple hundred, I don't see why you couldn't do this for like really, really big problems. So, I do know someone who solved a billion variable LP, just for fun. So, not using these methods, use direct methods. But it took one of these blue gene, it's an entire room full of computers. And each iteration, I think, it was either like an hour or 2 hours per iteration. And I asked him how many, what algorithm to use. Same one, primal dual, everybody else used. How many steps did it take? And he goes, same, 21. So, but that's like a day and a half or whatever it was. So anyway, so I think there's no reason to believe that these things won't go to much, much larger things. If you need to go to these large systems, I think it'll work. Okay. And any questions about this stuff? Like I said, we'll arrange that you will have personal experience with CG. And we'll arrange for your personal experience to involve nothing more than just a handful of lines. But you'll do CG, you'll run it, you'll solve something big, and then you can say you solved CG, or you solved a giant system using an iterative method. So, I'm just curious, actually, how many people have seen this stuff in other contexts? Where'd you see it?
CMU courses.
Oh, CMU, sure, yeah, that's like whole courses, right? Yeah. Okay.
Finance.
In finance, really? Which class?
Back home, Smith.
Oh, okay, at KTH.
Or Nietzsche.
Oh, Linköping, sorry. Oh, sorry. I'm mixing up my Swedish students. Really? So CG for truncated Newton and CG, or just CG?
Or BFGS.
BFGS. Well, okay. For some class on finance. That's cool. Okay. All right. The rest of you should just know about it. So maybe you'll never use it, but you'll do one, and then someday, 5 years from now, there'll be some giant problem, and you'll be banging your head, and you'll look up, and there'll be a big light bulb, and it'll say in the middle CG, and you'll get to use it for something. You'll get to use it for something, sure. Okay. All right. Next, now we're going to do another chunk of the class is going to be on it's a family of methods that have been around for a long time. These things go back into the 50s, and someday when I'm bored, I'm going to go back and actually find some of these things, these references. But it's like a lot of other things, like interior point methods as well. What happens is that for unknown reasons relating to marketing and just who knows what, fashions, all of a sudden, even though something's done for 30 years, the right person goes to the right place, and somehow each person there tells 10 of their friends, and then they each tell 10 of their friends, and this happens 3 more times. And all of a sudden, this thing bursts on the scene as if it was brand new. So that's the case for L1 norm methods for sparsity. You should know that it is in super duper fashion right now in many fields, in statistics and machine learning. It goes on, and in fact, in some cases, they're so damn sick. They're sick of it in like machine learning. Someone actually told me. He said, "No, we're in our post L1 norm stage," meaning that they're so sick of it, and everybody's done it, and they've already had their 300 papers on it at the last, NIPS or whatever it was, and so they're actually just they're moving beyond it, which is fine. Okay, so, and I'll say more about the history as we kind of get into it. And it's got different. Oh, the other thing to warn you about is it's got different names. I don't know if they're even in the slides here. The names you're going to hear about it are, some people just call them L1 norm tricks. Let's see, there's another, you'll find in statistics, you get lots of names, I don't know why. You get lasso, let's see, basis pursuit, several others. In machine learning, and you get things like SVM is support vector machine. People who do this will never admit that these are just L1 tricks. Trust me, they are. So they'll never, yes, and I hope some of you out there are watching this online and getting pissed off. So that's exactly why I said it, if you're wondering. So, because there's no one to piss off here. But anyway, all right. So, so support vector machines. Let's see. Oh, it's used in actually geophysics. Actually, I think was one of the earliest examples I can find. That's right from Stanford. That's 70s. That's John Claerbout. And there's a rumor of, and I've heard something about. I've heard something about some papers on antenna design from the 40s. I have to hunt those down using these methods. So okay, all right. So let's go over this. They all involve problems with cardinality. So now cardinality is just the number of non-zeros. Well, of course, it's the size of a set. But the cardinality function on a vector is simply the number of non-zeros in it. So, these come up a fair amount. They're actually hard to solve exactly. A lot of them are NP hard. Some of them people have shown that. Others not. Some might be easy, but there's a very limited number that are easy. There's simple knapsack problems and things like that. But the vast majority of these things are hard. Okay, so the other interesting thing about it is that there's a simple heuristic that relies on the L1 norm. Oh, I forgot to mention my list of fancy names. Compressed sensing is one that's making the rounds in statistics and applied mathematics, so you'll hear that. And maybe there's at least one or two other. It's got lots of names, but as I think of them. Oh, here's some right here. Okay. So it's been used for a long time. In engineering design, it's been used for a while. And we'll see where that comes up. It's been used in statistics. Again, there's a Stanford connection because the originators of this are at Stanford. Let's see. It's also related to robust estimation statistics. That goes into the 70s. Support vector machine and machine learning. This is from the maybe 80s or even maybe early 80s. It's total variation reconstruction and signal processing in geophysics. This again, like support vector machine, do not, if you see a person who does total variation reconstruction, don't say, oh yeah, that's, or actually do say, oh yeah, sure, that's just an L1 trick, because it'll really piss them off. And compressed sensing, that's the newest name for it. Okay. There are some new theoretical results. They are very cool because it really didn't occur to anyone that you could actually say anything about these methods. Those are very cool. I'll mention them, but needless to say, that's not going to be our focus. Okay. So cardinality of a vector, it's actually a separable function. So it's a sum of, it's this. It's actually the sum over all xi's of card of xi. But card of xi is nothing but 0 or 1, depending on whether the variable is non-zero or not. That's quasi-concave on r plus to the n, but not rn for what that's worth, which is not much. Because that would tell you that if you wanted to maximize the number of non-zeros, you could do it of some positive things, but that's kind of silly. Otherwise, there's really no convexity properties, and it arises in lots of problems. And let me just, I know this is kind of obvious, but I'm just going to draw the picture of the function just so we all know what it looks like. It looks like this. Here's x, and it looks like this. It's that, and then that. So this is, that's pretty non-convex, I think you'd have to say. Actually, we'll leave that picture up because it's going to, the whole thing's going to be highly implausible. Why these things work. Okay, so convex cardinality problem, it's a problem that would be convex, except cardinality comes into the problem somewhere. And it might come in the objective, but it also could come in a constraint. And these are really interesting. These are very interesting problems. So is this one. This says the following. This says, find me the sparsest vector that lies in a convex set. Boy, are there a lot of applications of that. For example, C could be the set of coefficient vectors that explain your data within some reasonable level of confidence. Okay? So these are then this says, find me the simplest description, explanation. Find me the simplest model. So that's what this is. So this is even, I mean, that would be like Occam's razor or something like that. It comes up in engineering design as well. So here, for example, the x's are often things like, widths or something of wires, let's say in a circuit. And then if a wire has 0 width, it means the wire isn't there. So it's basically saying, make me a power supply distribution network or something, or a clock distribution network. Obviously, you can't give a tree, because if you give a tree, you can't remove any wire segment. So you give a mesh. And then you're basically saying, find me the sparsest thing that will actually satisfy all the specifications. Okay? So this comes up lots of places. Another good example would be, design me an FIR filter. And these are the coefficients in the filter. What's cool is, if I have a filter and it only has something like 14 non-zero coefficients, 0 coefficients, I don't have to, if I can build now custom hardware that will just have 14 multipliers, I mean, or that could be in space or time, but you get the idea. You can make if a sparse FIR filter is one, you can implement in hardware very quickly. Actually, software as well, if you do it the right way. So, all right, it comes up in lots of cases. We'll talk about all of them. This one says, choose me no more than k of these coefficients. Okay, so how do you solve these problems? Well, the first thing is this. If you fix the sparsity pattern of x, okay, of which there are 2 to the n. So to fix a sparsity pattern says that for each component, it's either on or it's either non-zero or 0. There's 2 to the n choices like that. One choice is, of course, x equals 0. The other choice is x is full. So all things are there. There's 2 to the n sparsity patterns. But if you fix the sparsity pattern, you get a convex problem, and it's all over. Now, what this says is that if n is, let's say, 10, these cardinality problems can be solved immediately and globally, because you just solve 1024 convex problems, and you're done. Everybody see what I'm saying? And in fact, there's tricks there. You can even do it faster than that if you know what you're doing, because, for example, you can do things like this. Once here, suppose we want to find minimize the cardinality, the sparsest x that is in some set. This might be some design. Once I have found, if I have ever found an x with a cardinality, say, of 8, I never have to look at, obviously, there'd be no reason for me to look at any sparsity pattern that has more than 8, right? So you can often trim a large number of these things, even if you're doing direct enumeration. But the point is, you can simply do direct enumeration immediately if there are, for example, just 10 variables. Or 20. 20 is a million. That's overnight or something. Or in C, it could be some reasonable amount of time. Okay. All right. Now, the general problem is NP hard. That's actually quite easy to show, and it's not that relevant either. Now, you can solve these methods globally by a branch and bound method. We're going to do that later in the class. These are global optimization methods. And these things, they can work for a particular problem. And this is going to be the global solution. But in the worst case, these things reduce to checking all of the sparsity patterns, or at least many of them, or something like that. So these methods are actually heuristics. So there's a very good way to write these out as a Boolean LP, a mixed. I mean, there's a way to write these out. So a Boolean LP looks like this. You minimize a linear function subject to linear inequalities, but these x's are simply 0, 1. Now this problem here, you can embed, essentially any combinatorial problem can be embedded as a Boolean LP. I mean, any. And with a reasonable embedding. I mean, not one that grows size or anything like that. So, you take your favorite 3-sat traveling salesman, and I'll easily write it out this way. Now, if you want to see how to do it, it's actually pretty it's pretty straightforward. What you do is this: is you write down this. You write minimize C transpose x such that x less than b, and then you write the cardinality of x plus the cardinality of 1 minus x is less than n. Okay, less than or equal to n. Now, what's interesting about that is the only way that will work is that the xi's, either for each entry, either this one is 0, either that's 0 or that's 0, and that's the same as saying x is either 0 or 1. So it's a very quick embedding. Okay. I mean, not that it matters much. Okay, so now I want to talk about applications. I already hinted at this, but here's one. Oh, and by the way, I think these methods have not diffused anywhere near the extent to which they should have, right? Because what's happening is there's a lot of work on this. You know, some people know it, but they know it in a weird way. Like if they're in statistics, they just do SVMs or something, or L1 regularized this or that. They haven't really internalized this as just a completely general heuristic, powerful heuristic for getting sparse things, period. And there's lots of people poking around who could use these things and have no idea about these methods. They go to Google. The next thing they know, they're reading some fantastically complicated math paper with a result saying that if you do this in some incredibly special case and something's bigger than something else, then you'll actually get the global minimum with overwhelming probability or something like that. And that's not what they needed. In fact, was simply an excellent heuristic for solving sparse problems or something like that. So anyway, all right. So sparse design is this. This is the set of the set of vectors that satisfy a bunch of specifications, and you want the sparsest design. And so you can have FIR filters. Like I said, one of the first applications of this was antenna array beamforming. And here the zero coefficients correspond to unneeded antenna elements. So truss design is another one that's actually very wide. This is actually not only this is actually now has huge commercial impact. So there's a whole industry that does this this kind of stuff, and it's not just trusses, but all sorts of mechanical stuff. And here, zero coefficients correspond to bars that are not needed. Wire sizing, I already mentioned that. Now, what's interesting about these applications is, for example, let's take the antenna array design thing. So what you do is you start with, you say, here's where I'm going to put my antennas on something. And you say you start with 1,000, and someone says, well, you can't possibly put 1,000 antenna elements there, because first of all, we can't afford you can't afford that many. They won't even fit physically. You can't even fit them all there. The second is, you have to have an RF amplifier for each one, and blah blah blah. It goes on and on. And then you say, no. These 1,000 antenna array elements, you should think of them as possible antennas. I have absolutely no intention of using 1,000. In fact, I intend to use, let's say, 17. So then you say, but then why are you using 1,000 here? And you say, because this method is going to pick which 17 I'm going to use. And the same in truss design. You make something and you put 10,000 trusses or 20,000 bars in the truss. You have no idea, you have no intention of building a truss with 20,000 bars or 200,000 bars. You're going to let this thing decide on the 132 bars it's going to use. And that's a reasonable truss. So, okay, so this is kind of obvious. In statistics and modeling, it's pervasive, absolutely pervasive. I mean, and it's completely fundamental as well. It basically says the following. Oh, this would be a simple one. This says choose k columns of A to get the best fit with B. So, and that's a k-term model. And again, here you could do this by simply enumerating all n choose k choices. This is quickly gets out of hand if k is more than a handful and n is big, and so on and so forth. The variations would be choose me the minimum number of columns, which allows me to get a good fit. You could put it this way. I mean, there's lots of variations. This is regressor selection. By the way, this could be quite interesting because the columns of A here actually are regressors or features. And so you're actually doing, this is in, other people in statistics would call this, or machine learning would call this feature selection. So this would be feature, and you could throw in all. So what this means is it actually kind of turns a basic principle in modeling on its head. So let me exaggerate here, but say that basically as of 10 years ago, or before these methods were proliferated, the basic story in modeling goes like this. You say, I want to predict, the next term in this sequence. I have this sequence here, and someone says, fine, you construct a model, and you construct some like autoregressive model, and you say, I'm going to make a linear combination of the last 10 entries or something. Or it could be the last 10 entries plus weird quadratic terms plus sick things that your domain experts throw in there. Like they say, oh, here's an interesting feature. How about this? The highest value in the last 5 steps. You know, who's to say? How about the spread? The largest minus the smallest value. How about some weird time-weighted maxim? I mean, you can go nuts. By the way, this is all good from an employment point of view for the experts, right? Because if it takes the experts to generate all these features, that's great. But then you say, no, wait. Oh, obviously, the more features you add, the better you can fit your data. So if I give you a pile of data, and if I give you 100 data points, and I have like 100 features, then generically, I'll be able to fit it exactly and say, wow, I'm doing really well. That's stupid. It will have no generalization ability. And you would verify that by cross-validation. So you'd take your data, have 2 sets. You could even be formal about it, not even allow the person developing the model even access to the other one, and then you'd try out this way and you'd find overfit. And someone says, no, so the problem is you need the expert to choose a small number of features. Everybody following this story? So this is modeling, statistics, whatever you want to call it, as of 15 years ago. The story is everything comes down to choosing the right features. You get the right, and a small number of them too, by the way. So notice that puts the burden on the modeler. So that's the idea. And how would they do it? They'd sit around at home or whatever, or they'd actually have their grad students do it more likely. And they would try various combinations of things. And someone would say, oh my God, I got an amazing fit. It turns out that the volume minus the maximum minus the spread, blah, blah, blah. If I throw in these 6 features, I get an extremely good prediction of this. Everybody see what we're saying here? Okay. All right. So this completely turns it on its head. This basically says you can do feature selection. And what's super cool about this is A could be fat. If you have a fat A matrix in a general regression problem, that's just stupid. Automatically you're overfit. You're way overfit. There'll be lots of combinations that will reconstruct your data with zero error. They will have no generalization ability, but so fat is totally uncool in a fitting problem. Okay? So now here it works fine. What you do is you have something like 100 measurements and you give 10,000 features. So not only are you doing a bad thing, but you're doing it by a factor of 100 to 1. Everybody see what I'm saying? You're so overfit, it's ridiculous. But what you do is you solve this problem, and you either put a cardinality or you solve one of these problems here. And what those 10,000 features are, you have no intention to use 10,000 features to fit your 100 data points. Because you could fit them in a huge 9,900 dimensional null space of ways. You could fit them exactly. So what you're actually saying here is the following. These are 10,000 features. Most of them are probably completely irrelevant. And in any case, I'm not authorizing you to use 10,000. You may choose 30 of the 10,000 features. And that's exactly what this problem would do. So, by the way, the implications of this, I think, are going to ripple for the next 10 years. It's going to completely change modeling and a lot of other stuff. Everybody see what I'm saying here? So this is normally people talk about this at a much lower level, or everybody knows all these things, but I actually haven't heard people say it this explicitly. But everybody got this here? So you could do wild, and then, by the way, it's interesting. You have to totally change your thinking. If someone says, for example, I want to fit this data with a polynomial of these things, and someone would say, well, that's a pain in the ass, it's not going to work well, because if you have 10 variables, you want to fit a polynomial, linear is fine. That's 10 coefficients. Then you go to quadratic. How many coefficients you got? Come on, a quadratic in 10 variables? How many coefficients? I'll accept 2 answers, one of which is wrong, but not it's only off by a factor of 2. It's about 50, right? You have 50 coefficients in it. And then you go, well, how about cubic? Well, then you get 1,000 divided by 3. You get 160 or something like that in a cubic. And so the problem is, if you have limited data, when you do if you do generic polynomial fitting, you just get piles and piles of coefficients. Everybody see what I'm saying here? Okay, so this sort of changes that, because you could do these methods with sparse data. You can fit a polynomial. It'll be a nice sparse polynomial. It might turn out there's some sick polynomial degree 4 that this thing picks out that works really well. So, okay, well, I think I've said enough about that. Sparse signal reconstruction, this comes up. I guess there's people doing it. No. There we go. There's one. There's another one, though. There we go. Okay, there's 2 at least. Okay, so sparse signal reconstruction goes like this. It says estimate a signal. You're given some noisy measurement, and you're given the information that X is sparse. Okay, that's like prior information you're given. That's that's what you're given, and that comes up in a bunch of cases. Like it could be faults, anomalies, which I guess it is in your case. What is it in your? Oh, it's sparse coefficients in the radon transformer. It's going to come up a lot. Okay. And if you want to do a maximum likelihood estimate, if I tell you that something has only k non-zeros, you would end up minimizing this subject to that. I mean, you can't solve this problem, but you're going to do an approximation of it. So, and this is actually very important. You should think about this, about sparse priors. It's very, very interesting to think about. And I'll give you an example. If you go back to sort of the last, if you go back to sort of the last century, everything is based on kind of least squares. And if there's a statistician who says justify that, you would say Gaussian or something, and then that would turn into some now statistically defensible reason why you're using least squares. Right? That's how these things work. But sparsity doesn't really come up. So sparsity would come up, and once you start thinking about it, you start realizing, well, there actually are lots of cases where a signal model is that it's sparse. One would be like, set commands or set point commands or something like that. If you build some sort of controller for this based on all the standard stuff, you're really saying that the input is some Gaussian process. But in fact, what you really might think or want to say is something like this. No, the input actually is constant for long periods of time and then switches to another value. That's the way set points and commands actually look. That's sparsity. So that would be that kind of thing. Okay, okay. Estimation with outliers is another a beautiful example, and it works like this. You have yi is ai transpose x plus vi. This is just a linear one to make it simple. The vi's are our friends that were with us last century. Those are our nice Gaussian noises, our catch-all. It's basically, this is our statistical excuse for using least squares. That's what this means. Okay? But then you have this other weird noise, w. And the only thing you assume about it is that it's sparse. So for example, it has fewer than k entries or something like that. And basically what these are is these represent either anomalies, outliers, or bad measurements. And this comes up a lot. So basically this says that, every 100 samples, the measurement you get is just completely unrelated to, because you don't assume anything else about W. And of course, by choice of this thing, I can make this thing anything I like. So it's something that's just simply unrelated to the input. But you're not told that. So you're not told that. You're simply told, I'll just give you the measurement. By the way, if these are all on the order of on the order of 1, and W is like 10 to the 5, this is not a hard problem because a measurement comes in, they've all been coming in around plus minus 1, and one comes in as 10 to the 5. It's a good guess. That's an outlier. Anybody can handle that. Okay. The really insidious cool way is this, is when the bad measurements come in, they have the same statistics as the good ones. So if a measurement of 0.8 whatever is plausible, and the completely bad measurement comes around and it's 0.8, that's much trickier to do. Actually, you'll find out these methods that we're going to look at here, they'll handle that like amazingly well. I mean, amazingly well. Where I don't know of any other method really that would sort of get close to doing this. Okay. Anyway, so you get this. You're basically you're estimating the set of outliers and so on, and it would look like a problem like that. By the way, you'll see that when we replace this with an L1 norm later, this is just going to recover robust statistical methods that have been used for 25 years in statistics. So, okay. Here's a very interesting one. Suppose you have a set of convex inequalities, and they're not feasible. They're not mutually feasible. So, for example, let's do this. Let's make these a bunch of design requirements. Well, let's make it a circuit. So this is a power limit, an area limit, a timing constraint, or something like that. They're not mutually feasible. They cannot be satisfied. So the intersection is empty. Then you'd say this. You'd say, well, First of all, that's good to know, because you go back to the person and say, your specifications are infeasible. And they go, well, you can't do it. Maybe I need another designer. And you go, oh no, wrong. This problem is convex. And when I say it's infeasible, I don't mean I failed. I mean everyone will fail to do it. And they go, well, so I mean, fine. And then they go, that doesn't help me. Of the 17 constraints, please come back with a design that violates as few as possible. So that's how you could do it. And in fact, what you could do is you could classify your constraints into the ones that are non-negotiable. And you could then have the other ones that you really wanted but can't have. And for that latter group, you say, okay, of these 10 or 50, if I said 10, it's no problem, because 2 to the 10 is 1024, and that you can solve immediately. So I should have said, of these 100 inequalities here that I'd like to have, please find me a solution that violates as few as possible. Everybody see what I'm saying here? Okay. All right, so you would do this. You'd say minimize the cardinality of a vector t subject to fi of x is less than t and t is positive. Now, what happens here is this, is whenever t is 0, it means that the ith inequality is actually satisfied. If you can't satisfy the ith inequality, t is sort of like a little fudge factor. So t positive means you've been given some slack here. So this thing here will immediately and directly solve the question of finding the minimum number of violations. Yeah, by the way, these are really useful. By the way, we'll see also, you've already seen this, you've used it, we've talked about it before. It's an L1 phase, it's a sum of violations phase 1 method. So, but it's good to see all these in the same context. Here's one, linear classifier with fewest errors. So we'll do some machine learning type stuff or whatever. So I have a bunch of data. I have x1, y1 up to xm, ym. These are vectors, and then these are binary labels, so they're plus minus 1. And what I would like is I would like to find a vector w and an offset v so that sine of w transpose x plus v is y. Now, approximately equal means something like you make as few errors as possible or something like that. You do it right if yi times this thing, actually if yi times, if the sign of this is, well, if you make this positive, that means doing it correctly. If these have opposite signs, that means you've messed up. So if you want to find the w and v that give the fewest classification errors, that's basically you have a bunch of things that are labeled. If you can get 0 classification errors, that means you can put a hyperplane between the points. But now you want to put the hyperplane there that has the fewest number of things on the wrong side. And that would just be this problem here. Now I should remind you something here, and that is that not one of these problems that we're writing down can we solve. So that's important to understand. They're all hard. So you might ask, why are we writing these down? Right? Oh, we can solve them in some cases, right? If there's 10, if I've got 10 weights, I can solve this, okay? If this is 10 features, I can solve this problem by solving 1024, if m is 10, I can solve 1024 convex problems, and I will get absolutely the linear classifier that has the fewest number of misclassifications. But if m is bigger than that, you can forget it. We're writing these down this way because later we're going to see a heuristic is going to apply to all of them, and you're going to get good methods.
Why is there a 1?
Yeah, why? Because to make it right is to make this positive, to make this thing positive. Yeah, so you can't write down a strict inequality in a problem. Well, you can write it down all you like. It won't do the right thing. You need strict positivity. However, that constraint, when I make this strictly positive here, is homogeneous in W and V. And therefore, to say that it's positive is exactly equivalent to saying that it's bigger than or equal to 1 by scaling W and V. So this is a standard trick for that. Yeah. Homogeneous problem with a strict inequality, you kind of replace it with a 1. Okay. Here's a variation that's actually extremely interesting. This one is a variation on find me a point that violates as few as possible. In fact, it's the dual. And it works like this. I give you a set of inequalities which are mutually infeasible. And what I want to do is the following. If someone says, if you said, well, I have 28 specs, let's say on, phase margin, power, rise time, slew rate, blah, blah, blah. You say, I have 28 of them, they're mutually infeasible, no one can design that amplifier, period. So then you say, okay, the question then is what's messing you up? So, and let's figure out what would be a powerful statement. A powerful statement, if I gave you 28 inequalities, would be to say, well, actually, as it happens, inequality number 14 alone is infeasible. That's a very powerful statement, right? Because it means that basically you have to deal with that one. You'd have to, if you're going to relax one, you have to relax that one. Everybody see what I'm saying? A slightly less powerful statement would be, well, 14, 22, and 37, those three together are mutually infeasible. And the weakest statement I could make is that they're all mutually infeasible, but if I remove any one inequality, they become feasible again. Everybody see what I'm saying here? That's the weakest statement you can make. So basically, the smaller the cardinality of a subset of infeasible inequalities, the stronger the statement, the better you have identified what the problem is, what's causing the infeasibility. Okay, so how do you do that? Well, you do it as follows. You look at the dual function, that's g of lambda, that's this thing. That's, again, by homogeneity, has to be bigger than 1 and lambda positive. And so what you'd do is you'd minimize the cardinality of lambda subject to g of lambda bigger than 1 and lambda bigger than or equal to 0 here. If lambda is 0, it means that if lambda I is 0, it means you didn't use fi in constructing your proof of infeasibility. And it means, so a sparse dual certificate basically corresponds to identifying a small subset of mutually infeasible constraints. So that's how that works. Okay. We'll do another one, is portfolio investment with linear and fixed costs. So let's see how that works. We're going to, we'll take long positions. So we're going to invest an amount xi, and they're going to sum up to b here. Well, we'll get to that in a minute. No, that's our budget. Sorry, they're not going to sum up to b because we're going to have to buy. We're going to purchase these things, and the way that's going to work is this. So here, I'm going to have a trading fee, which is sort of alpha. This could just be a scalar. It doesn't really, a scalar times 1. So if I buy an amount, I'll charge you something like 1%. But also, if you buy a stock at all, I'll charge. If you initiate a trade, I'll charge you $50 plus 1%. Okay? That would be for like a sad consumer like us or something like that, right? So that's the way this would work. So the budget constraint says this. Let's see. That's the total amount of the stock that you that's the value of the stock you purchase. That's your trading cost, and that's less than your budget. That's it. And and you just say, well, we'll just do a simple 1952 mean variance problem. So your mean return on the investment is mu transpose x, and the variance is x transpose sigma x. And so you might say something like this. I want a minimum return of R min, and I would like you to minimize the variance, the risk of this portfolio. Okay? And then this is the constraint that says that you're sort of within budget. Now, of course, when you do this, this will be equals here. Okay? So that's a relaxation. It doesn't matter because you can't solve that because of this thing here. Now, this one is actually quite interesting. What it says is, well, let's even just talk about it intuitively for a bit. If you invested in one stock, then your fixed trading fee is going to be very small. It's just going to be beta. So you're only going to have lost, let's say, $50 if you invest in one. Now the problem with that is you're going to get high risk. The whole point investing in a couple of them is to have the risk go down. So if you have a couple of assets with a correlation coefficient that's away from 1, I mean ideally it would be negative, in which case you could hedge, but that wouldn't actually happen. But let's suppose they were, a reasonable correlation coefficient was not, 0.9 or 0.8. If you invest in 2, your risk goes down here. Now the problem is if you invest in 2, you're paying $100 in fixed fees. So this is kind of the idea. If you solve it if you set beta equals to 0, that's a convex problem. And you can actually find out. And that'll generally, by the way, invest in a bunch of different things. Okay. Let's do piecewise constant fitting. So here you have a fit, a corrupted. You want to fit a corrupted signal x corrupted by a piecewise constant signal x hat with k or fewer jumps. So in other words, I have measurements I have a signal which I believe to be piecewise constant and to make a jump every so often. And over my time of interest, I believe it's going to make k jumps, but no more. Okay? I give you very noisy samples of it, and you want to fit it with a piecewise, with a signal that's piecewise constant. All you have to do now is this. You form a difference matrix, and dx hat is actually the difference vector, and the cardinality of that is the number of jumps. So if that's n minus 1, it means that at every step x hat changes. If it's 0, it means that that x hat is constant, it's flat. Okay, so your problem might be this. Get as close as you can to the corrupted signal with a piecewise constant signal that has k jumps. Okay. By the way, some of these you could actually solve. This one you could probably actually solve. That one's probably not hard. You can also do piecewise linear fitting. So piecewise linear fitting, you do the same thing, but you take a double difference operator. So a del square operator or something like here. So you take the second difference, because this thing gives you the second difference. And a jump, if del x hat is 0, it means that x hat is the average of its two neighbors. And that means there's no curvature there. There's no curvature. If this is sparse, it says that the signal x hat is piecewise linear. So this is a piecewise linear signal with k jumps. So, okay. Finally, we'll get to the L1 norm heuristic. It's embarrassingly simple. The simplest version of it, we'll look at much more sophisticated ones later. But the embarrassing one is this. You simply replace the cardinality with some multiple of the 1 norm. It's that simple. Or you add it to the objective. And then gamma is a parameter that you use to tune things. Now we're also going to see weighted ones like this. But actually, before we go on to that, I want to draw the picture over here just to show you how completely ridiculous this is. So here it is. Here's the actual function. Here's the cardinality function. I'll just draw it like that so you get the idea. There's the cardinality function. And this heuristic says approximate this function with an absolute value. So now I don't think there's no one. There are very few people who would argue that this is a good approximation of that. I mean, that takes some serious storytelling abilities to convince someone that that's a good approximation of that. And in fact, when you look at this picture, because that's all you're doing, you're replacing a function that looks like this. It's 1 everywhere, drops to 0 right at 0. You're replacing that with an absolute value. So whole thing looks highly suspect, highly implausible, doesn't make any sense, but that's it. But remember, the same thing goes with Lagrange duality. I don't know if you remember that. You approximate your irritation function that looks like this with slope. So, and that worked out. Here it's not going to work out. It'll be a heuristic. Okay. So let's just do an example here. We start with this hard problem. Find me the sparsest x that's in some convex set. The heuristic says minimize the 1 norm of x subject to x in the convex set. This is convex. That's an easy problem to solve. And what can you say about it? The solution of this is not the solution of that. We'll see what you can say. There's cases where you can get a bound on this solution from that. And there's a very, very small number of cases, extremely special. Basically, C is an affine set, so it's just equality constraints, in which there's actually a statement you can make. However, I mean a statement that's actually true. You can always say this. This seems to work unusually well as a heuristic. This and variations. So as a cardinality constraint problem, you could do many things. You could add this way and then sweep beta. You could also add it in here. And you would adjust these numbers so that the cardinality is less than k. And I think I'll mention one quick thing. I think we'll do one example and then we'll quit. So polishing is quite interesting, and let me explain what that is. It's not universally used. Statisticians don't do it for some reason, and they tried to explain it to me, and I didn't get it. Apparently, it's bad, but anyway, at least in the context of their problems. But for other applications, it's not. It works like this. You use the L1 heuristic to find an x hat with required sparsity. Now, once you've done that, you fix the sparsity pattern, you go back and you solve the problem again. That's how that works. And that's called polishing. That's not a standard word. I just made it up. So, but it sounds like a good word. So a good description of it. Are you doing that? You will now. Okay, good. So, good. Yeah, it doesn't take much. Okay, so to do this, and I think what we'll do is maybe we'll quit here. Actually, what I would like to do is just to get to a quick example, and then we'll come back just for fun. There we go. Okay, so we're going to do a quick example, and then just so I showed you one. So we want to find, this is the regression selection problem. We want to select columns of A to fit B with, K of them. And so what we'll do is we'll replace this. We'll do an L1 thing. You actually, you add this plus lambda times the 1 norm of x, and you trade it off. This is a tiny little problem. Although it's already big, I could actually do this if I wanted to, because 2 to the 20 is about 1 million. And so this one, I could actually find the global solution. In fact, I believe this is the global solution. This is the global solution calculated with 1 million by solving 1 million least squares problems. What this shows, the dash curve is the solid curve is what happens if you do the L1 heuristic with polishing. And you can see it works pretty well. Everyone agrees sort of here. But what happens now is you can see any gap between these two is where you've missed the global optimum. What's interesting is, for example, over here with 3, you actually get the global optimum. And in other places over here at 1, you get the global optimum. I guess you nailed it at 6 as well. But notice that you're never really very far off. So, and considering that the effort in calculating this curve, in this case, is off by is a factor of 10 to the 6, you'd have to say it's not bad. I mean, this is not bad. So so for solving it 1 million times faster, you get close. Okay, so this is a good time to stop, and then we'll continue next time. And before you leave, there is a tape ahead tomorrow, 12:50, 2:05. It's on the course website. We'll quit here.